you onto the bigger blobs. Okay, so all right, so we talked about multiplexers. So in that I explained you we can use the two pass gates to form two input multiplexer or 2:1 multiplexer. So you see pass gate number 1 and pass gate number 2, I use these two. And look at the circuit arrangement. I have a data line D0, I have a data line D1, and I have a control signal S. I call it S. So when I have a control signal, I assume its complementary is also available. S is available, it means S bar will be there. So based on the control logic, if S equal to 0 or S equal to 1, one of these pass gate will be active. Based on that, D0, either D0 or D1 at a time will transfer or will connect to output Y. This is how I told you that the circuit of multiplexer works. So that's the symbol. When S equal to 0, D0 connects to output. When S equal to 1, D1 connects to output. That is 2:1 mux. So 2 input line and 1 output line. Here was the truth table. And you see, this is nothing but your Boolean function. So in the previous session I explained to you that any Boolean function you can implement using the compound gates, and any Boolean function you can implement using the pass gate also. So this is the way they have implemented. What about I ask you to implement this using the compound gate? What you see here, let's assume that S bar is 1 literal and D0 is 1 literal. S is 1 literal and D1 is 1 literal. So I see there is an ANDing operation here. So I can say that I have, let's say, 2 transistors and MOS here. Here I say S bar, and here I say I have D0. Okay, and then I have another one. So I would say I have this one again. You see, they are like this. This is S and this is D1. And they are ORing, they are making the ORing function, so these pairs are in parallel, and that's how my ground is, right? Will it work like this? There is no bar here, so how to implement this? Any question? Any comment about that, how to implement this Boolean logic using this CMOS gates? Can you do so? So we'll see in the next slide. Let's say how we are doing it. Look here. This is one. So basically this why not used PMOS? You can unmute yourself instead of using your comment section, right? You can unmute and speak out. Manikanta. Okay, so why not use PMOS? So here we have used the PMOS. So because when we use the PMOS in the logic up here, we'll use the PMOS now. So that will be a pull-up network. Yesterday we see that, right? So here it's the circuit diagram, but then the output will be the complementary of this function actually, right? So in that case we are basically doing the inverting multiplexer, you know. So you see in the symbol also we have used the bubble here, you see, and in the previous diagram we don't have a bubble here, right? So this is the circuit diagram or logic diagram of inverting mux. But if you want to like implement this logic, then you can go for the pass gate implementation also, right? For the pass gate. But for the compound, you first need to implement this one, so it will implement this function, and then you will have to put the NOT gate here to get the normal function without a bar, right? So that's the way you basically try to implement the things. Now there was one more approach, if you recall from the previous session, the tri-state approach. I explained you already what is tri-state. It has 3 states: logic 1, logic 0 and high impedance. So I have taken the same I have implemented this boolean expression using the tri-state. So I have two inputs and I have control S and its complementary S bar, right? So first tri-state, that's the first tri-state inverter, and there is the second tri-state inverter. So output of this first one was fed to the second. So I called it, if you recall, mux using the tri-state logic, and I can verify its operation when D1 reaches to Y and when D1 reaches to Y based on what I apply to S equal to logic 0 or logic 1. Based on the switching will happen, and I already know now how tri-state works, and accordingly the circuit will work as a multiplexer 2:1 using tri-state logic. So there was the first implementation, there was the second implementation, and this is also your third implementation, right, using the pass gates. So if we compare these two on this slide, this one and this one, which circuit implementation is more compact and faster? Compact means less number of logic gates or less number of transistors. Faster means it has a higher speed of operation, right? So I said that, look here, how many wires I need? D1 not here, and it's then D1, that is second wire, then third wire for S, and the fourth wire for S bar, right? How many I need here? D0 and D1, but D0 is connected directly to both the transistors and D1 is also connected both the transistors. So I save two wires here. Here I need separate wires. D0 comes here and also to its complementary, right? Here I'm connecting it to both NMOS and PMOS at the same time. So I save two wires. Similarly for the S, I have separate wires, right? So at least two wires I could save in this circuit diagram. So that's why this tri-state approach is more compact, and obviously it's a faster because it has a less internal wires. So less internal wires means there will be a less delay. Less delay means higher speed of operation. So that was the truth table. We saw that for this one we already know now. S is equal to 0, then I don't care what is at the D1. Whatever the D0 is at logic, that is connected to the or passed to the output. When S is equal to 1, I don't care what is available at the D0, but whatever is available at the D1, D1 is connected to the output. So that's how the multiplexer will work. So these all logics that I explained to you so far, they are called as combinational circuits. Or logic. Combinational logic, it means you see whatever the input is, that goes to output, and output depends on what is available at the input. It doesn't have any feedback or a mechanism to store and memorize the previous information. For instance, what was the previous value at the input, right? And it doesn't have a clock. So there is another category we'll see now, that is called as sequential circuits. But before that, this last slide for the combinational one. What if I want to implement 4:1? So I have 4 lines, 4 data lines. Each data line will carry the logic 0 or 1, 0 or 1, right? So you see I have used 2 pairs, 2 different multiplexers, 1, 2 here, and the third one. So 2:1 mux, and each mux I know they can be implemented using pass gate, just before we have seen that. So based on, I have 2 control rights because this is a 4 input multiplexer, so 2 to the power 2, I have 4 input lines, right? And the control signals will be 2, S0 and S1. So what I do here, I will have a basic configuration 0 0 0 1 1 0 and 1 1. Based on whatever the logic available, the control, the each of these pass gates will be enabled. For the first two cases, this pass gate will help to transfer D0 and D1 to the output Y based on the first two configuration, and for the last two configuration this pass gate will be enabled and then it will connect to the Y through this one, right? So that's not important. Just what is important is to understand that we can create the larger multiplexers here. Similarly, there is this multiplexer 4:1. This is using the pass gates or using the multiplexers, and this is using the tri-state. So again you see S1 S0, S1 S0 bar, S1 bar S0 and S1 bar S0 bar. So you can just simply say that this is like 0 0 and this is 0 1, this is 1 0 and this is 1 1. So based on what level of control is, one of the data goes to output at a time. So this is using the tri-state logic. Okay. So now talk about the sequential circuits, as I said before. So we have understood what is the combinational logic, and now time to understand what is the sequential circuits, because here in such circuits we'll understand you have an input, you have an output, but the output depends on the present state of the input as well as its previous state. Okay, and these circuits are also characterized by the another signal called as clock, right? So when we will study the topic of static timing analysis and clock synthesis, these blocks like latches and flip-flops, they are the important building blocks, and a good understanding of them will help you to understand the layout that was constructed using these. Because when you will run the timing simulation, you need to understand what is happening at that level. So we'll see how this works. So we'll know that in combinational circuit, output depends only on the current inputs, right? It doesn't remember what was the past input or previous input. It just whatever the current input is, when the circuit switches, it connects the input to the output. But the sequential circuits has a memory. So it means their output depends on both current and the previous inputs. We'll see by some examples. So there are two examples. One is called latch and one is called flip-flop. And they are, remember, sequential circuits. So let's understand what is the latch. So right here you can see that here I know now this is my multiplexer, right? 2:1 multiplexer. So there are two inputs, one is here and second is here. I know that this multiplexer can be implemented using the pass logic or transmission gate, right? So I have understanding. Now to this 2:1 multiplexer, I have a data input. That data input can be held to logic 0 or logic 1. And I have a special input or special control that is called as clock. So when the clock is 1, I say that the circuit is active. Okay, and it means whatever the multiplexer acts as a door. So door opens when the clock is 1 and this data goes to output Q, right? When the clock is 0 or is not active, the door closes and the data is not able to transfer to Q. So that's the meaning of latch. It's called as 1-bit latch. So if you have 10 such latches and build a circuit, so that would be called as 10-bit latch circuits. We'll also see how these latches are used to create the flip-flop. So if I use 3 latches, Each can store one bit of information, latch 1, latch 2 and latch 3, and I have a clock signal. I have a clock signal to each of them. This is clock, right? So based on the clock I apply, and I have a data input D, and the output of it is fade to here, fade to here and fade to here. We'll see it in more detail. And this, let's say Q1, that is Q2, and this is Q3. So for each clock applied to the circuit, the data goes transfer from this place to another and another one. So we'll see how this works and all that. So remember, latches are used to build the flip-flops. So when the clock is 1, let us understand this operation. So now these mux, how I implement these mux? I use two pass gates, this first pass gate and the second pass gate. So you see, the rest of the circuit is similar here. Only this portion is the circuit diagram for the multiplexer using this pass gate 1 and pass gate 2. So what happens here? You have a data input D, and there is a clock and it's complementary. There is a clock and it's complementary here. So let's understand how the circuit will work. So when the clock is 1, so look at this diagram. When the clock goes 1, this pass gate acts as a switch and it closes. This pass gate acts as a switch and this gets open. Why? Because of the connections I have made here. Clock and clock bar here. So this goes closer. It means when the clock is 1, because of the switching, data D goes to Q, right? And this switch is open. So whatever the Q bar would be the complementary of Q, it cannot go back to here and go back here because switch is open here. So very simple to understand. So understand that when the clock is 1, D is transferred to Q. So we say that latch is transparent and D connects to Q. But when the clock goes to 0, so another circuit, this switch is open now and this switch is closed. So in the earlier, the data got connected to the Q, it will remain like that, okay? And the complementary of that, if let's say 1 was here, the 1 got here, and it means Q bar was 0 now. So this 0 will come here and come back to here, and it will become 1 because of the inverter here, right? So when the clock is 0, latch is opaque. Opaque means data, whatever the new data is available, 0 or 1, that cannot go back to Q here. So Q will remain to its previous state, right? So this was the switching diagram. What about the timing diagram? So let's say you have a clock. So this is the logic level 0. This is the logic level 1. So when the clock is 0, we know that, look at this diagram, the data D cannot connect to output Q. So what we see that D is 0. So Q was in its previous position, no matter. But as soon as the clock became 1 here, let's say, so it means when the clock became 1, at that time D was 1. So D got transferred to Q because Q became 1 now. Because D got connected to Q here. You see? Then D remained 1. So Q also remained 1. Because clock is 1. Clock is 1 all the time. But now here, clock went to 0. It means second circuit now. So D got disconnected from the output. So it means Q is not following the new value of D. So you see here, in the previous, when the clock is 1, D went to 0, Q also following the D, and it is following the D. It is following the D. But now clock went from 1 to 0. So D is 0, okay, but D now got to 1, but Q is not following the D because clock is 0 here. Simple to understand, right? Do you have any question on this D latch, how the latch will work? It's simply a 1-bit memory cell that operates on clock equal to 1 and clock equal to 0. When clock is 1, remember, Q follows the D. This mux allows the D to go to output, and when clock is 0, the latch becomes opaque. It means it doesn't allow D to connect to output, and output remains what it captured in the previous value of D. So such kind of latch is called as level sensitive latch. Such kind of latch is called as level sensitive latch. So what is level sensitive latch here? So you see in the timing diagram, this is the logic 0 level and logic 1 level. So when the logic level of the clock changes from logic 0 to logic 1 or logic 1 to logic 0 again, the circuit responds. And the state of the output, we saw that it depends on the level of the clock. Now this is the operation that I showed is called as positive level sensitive latch, because this clock right here, this circuit is working and responding when the clock is making transfer or transition from logic level 0 to logic level 1. So I am defining it as a positive level sensitive latch, and that is this working happening based on the logic I have applied here. Clock I applied to NMOS, clock bar I applied to PMOS. Clock I applied to PMOS and clock bar I applied to NMOS. What if I change the direction? Here is the clock bar and here is a clock. Here is a clock bar and here is the clock. Again then if I verify the operation, then this switch will be open and this switch will be closed for clock equal to 1, and this switch will be closed and this switch will be open for when the clock goes to 0. Such behavior can also be obtained, and that behavior of the latch is called as negative level sensitive latch. So remember, depends on the control. You can choose to design a positive level sensitive or the negative level sensitive. Simply, here is the symbol. Remember now, your data input D, output Q, and latch becomes transparent when the clock is 1. Transparent means D goes to Q. Opaque means D cannot go to Q when the clock is 0. Simple. Now once we understood the basic operation of latch, can we then use two latches? For example, latch 1 and latch 2. I have a data input here, and the output of the latch 1 is called as QM, and the output of the second latch is called as Q. I can also call it Q1 and Q2, but just for a simplicity I am calling QM is the output of first latch and Q is the output of second latch. And look the clock, how clock is coming. Clock is coming right here, and clock bar is fed to the first latch, which is the inverter clock, and it's complementary. So this is important to understand. So I know now the latch is nothing but 2⁻⁴ mux each latch, and each mux is pass gate combination of the two pass gates. Pass gate number 1, pass gate number 2. So that's my first latch. Pass gate number 3 and pass gate number 4 will consist of the second latch. Okay, and that's how I will understand. Now how is the control? Clock and clock bar, clock and clock bar, same fashion, but here the reverse polarity, clock and clock bar, clock and clock bar. So remember, based on how you connect the clock and its complementary to the pass gates, the circuit will respond accordingly. So what I am doing here, I have combined one negative sensitive and one positive sensitive D type latch. Why it's called D latch? Because it's data latch. It transfers the data from input to output. So I have to, and when I do so, this circuit is called as flip-flop. Okay, so each latch is capable to store one bit of information, right? And there is one more word I am introducing, this is called edge triggered. Edge trigger means now when you do the clock tree synthesis using your EDA tools and all that, this level sensitive positive or negative and the edge trigger sensitive positive and negative needs to understand. So what is level? This is called level 0. This is called level 1. So when you make a transition from level 0 to level 1, and again that's the level, remember always. And if I have such kind of represent, again this is I am making a transition from 0 to 1. Now this is level 1 and level 0. So I am making transition from level 1 to level 0. Now what is this? If I say like this, so I was at 0 and now I went to 1. So this is called edge, positive edge, 0 to 1. Another one is 1 and arrow shows that this is negative edge. So triggering of the circuit can happen at the levels positive or negative, and triggering of the circuit can happen at edge, positive or negative. So remember, so when I am building such circuit, I am also calling it as a edge triggered. It will respond to the edges of the signal, not the levels. Level means I will remain at this level all the time and the circuit will respond accordingly. But edge means circuit will respond only when I make a sudden transition from 0 to 1 or 1 to logic 0. So that's the reason. Why I'm not showing such kind of ideal clock or signal? Why I'm showing instead like this? This is ideal and this is practical. It means your waveform or the signal in the digital logic will always have some rise time and the fall time. This is called rise time. This is called the fall time. Okay, so that is responsible for the delay. We'll see what delay is and how it is computed. Okay, so you see now how to design a flip-flop. First latch, I will call it as a master flip-flop. Master. And the second, I will call it as slave. So in your undergrad syllabus, you might have studied that SR latch, then JK master slave flip-flops, right? D flip-flop. So D latch was nothing but a D flip-flop. In the earlier slide, I explained you D latch in just D flip-flop because it stores one bit of information. So SR, JK, and there is one more toggle flip-flop T. Toggle is also a latch, right? So all these were kind of cases that you studied. So it's basically they are all built from the latches, okay, which is used to capable to store one bit of information. Now let us understand how this circuit works and why is it called as master slave latch or master slave flip-flop. As the name suggests, the slave will respond or follow the master. That's why it will call as master slave flip-flop. We'll see how. So I know now, understand that if the clock is 0, right? So if the clock is equal to 0 logic, this is how the circuit will look like. This pass gate as a switch gets closed, this pass gate gets open, this pass gate as a switch is open, and this pass gate as a switch is closed based on my logic here. So if the D at that time was at logic 0 or 1, so this is basically coming to the output. So D was 0 or 1, the QM, which is the output of this first master, will become 1 or 0 because of this inverter. It will be just complementary. And then there is a broken link here. Switch is open, so data cannot go here. So whatever the Q was earlier at 0 or 1, it will stay there. And this logic is coming only to here, right, up to this point, and again it is again going to there. So it's basically staying at the previous value. Maybe in the previous cycle whatever the D was there, it got transferred to the Q, so it was just holding that value, right? But so that's what I am saying, that when the clock is low, the master latch output, which is the master, this is the master latch output, it will follow the D input. D goes to QM, simple. But the slave output, this latch, will hold its previous value, whatever it was. But what happens when the clock goes from 0 to 1? So now earlier clock was 0, now it became 1 here in this circuit diagram. So if it is 1, then all switch which was open, that will get closed, and the switch that was closed will get open. So you see these switches are opposite now. This got open, this got closed, this got closed, and this got open. So in the earlier cycle, the D came here, right? So QM, this is the output of the master, that remembers what was the D value. Now that value it will transfer to Q. So Q got equal to D. So whatever the D in the previous cycle, now it has a value with the Q, right? And it will stay there because the switch will open, right? Again when the clock becomes 0, so what happens? We come to this circuit diagram now. So new value of D comes here, and because this switch is open, and Q will hold the previous value of D, what was here in this cycle. So this cycle will continue always. So that's why Q is following the inputs from the master. That's why this latch is the slave and this latch is the master latch. And this is how this is responding at the edges of the clock.